This is Anisha from the Department of Computer Science. In this video, let's see what is Dijkstra's algorithm. Dijkstra's algorithm is nothing but to find a shortest path efficiently. In many real world situations, we often need to find the shortest, fastest, or least costly path between 2 points. So, for example, finding the shortest, fastest route from one city to another in a GPS, or like sending a data packets through the internet efficiently, or like determining the least cost way to connect different nodes in a network. So these problems are modulated using a graph. So whereas in graph, we have vertices, edges, weights. So in vertex, which represents the location, computers or entities, and the edges will represent the path, road or communication link between them. And at last, weight represents the distance, cost or time between the nodes. So to solve such problems efficiently, this Dijkstra's algorithm plays a central role. So now let's see what is the historical background of this Dijkstra's algorithm. So in 1956, during a coffee break in Amsterdam, a Dutch computer scientist, Edgar W. Dijkstra, conceptualized this algorithm mentally. So he aimed to design the simplest possible method to communicate or to compute the shortest route between two cities. So Dijkstra's brilliance was in creating an algorithm so simple that it would be executed mentally yet efficient enough to scan across computer system for decades to come. What is Dijkstra's algorithm? So let's see the core purpose first. The main goal of Dijkstra's algorithm is to find the shortest path from a single source node to all other nodes in a weighted graph. So it ensures the guaranteed optimal results, meaning the path found will always have a minimum total cost or distance. So, for example, if you are at one city and want to find the shortest routes to every other city, this algorithm helps calculate that efficiently. Let's see what is the key constraints. So the algorithm only works with the non-negative edge weights. So that is no negative distance or cost. So this is because the algorithm relies on a greedy principles. So once it marks a node distance as a final, it assumes the value cannot be improved. So if negative edge exits, this assumption fails and the algorithm may reduce the incorrect results. So for example, if one road has a negative distance, so which in real life might represents a refund or a reserve cost, so the algorithm can get confused and recalculate indefinitely. So to handle negative edge, another algorithm called Bellman-Ford is used. Next is universal applications. So Dijkstra's algorithm is widely used in across many fields because finding the shortest or optimal path is a common problem. So let's see three methods. So first is GPS navigation systems. So it will determine the quickest or shortest driving route between two locations. So to this we use a Google Map or any other navigation softwares. Next is network routing. So, to determine the most effective path for data packets to travel across the internet, forms a core of routing protocols like Open Shortest Path and ISIS. Next is optimization problems. So, it is used in a logistic and transportation to reduce cost, time, or distance. And it is also applied in AI for robot motion planning or game path finding. Let's see the core ideas. So Dijkstra's algorithm is built on a greedy approach, meaning it always expands from the node that currently appears to be the closest source. So at every step, it selects the most promising, that is, minimum distance node, and explores its neighbor to find the shortest path. So this approach ensures that once the shortest node distance is finalized, it will never need to be updated again. The process continues until all the nodes are visited or all shortest path from source node are determined. Let's see how it is processing. So first step is to initialize the distance. So at the start, the source node, which is the starting point, is assigned a distance of 0 since the path from itself to itself has a 0 cost. So every other node in the graph is assigned a distance of infinity. So representing that the path to these nodes is currently unknown. So this initialization helps the algorithm differentiate between the visited and unvisited nodes later. So the second step is to select the minimum distance. So among all the unvisited nodes, the algorithms picks the node with the smallest tentative distance. That is the current shortest known distance from the source. So this node is considered the closest node at that moment. A priority queue or mini leap is usually used for the effective selection. So the third step is to update the neighbors. So once the closest node is selected, the algorithm examines all its adjacent neighboring nodes. So for each neighbor, it checks whether the path through the current node provides a shortest total distance than one previously recorded. If it finds the shortest path, it updates the distance value for that neighbor. So the fourth step is to mark as visited. After exploring all the neighbors of a selected node, mark that node as visited. So once a node is marked as visited, it never revisited again because its shortest path has already been finalized. So this step prevents unnecessary recomputation and ensures efficiently. Let's see this in a graph. So for this graph, we will assume that the weight of the edge represents the distance between two nodes. So initially we have the distance from the source node to itself is 0. In this example, the source node is 0. So the distance from the source node to all other node is unknown. So we mark all of them as infinity. So 0 to 0, 1 to infinity, 2 to infinity, 3 to infinity, 4 to infinity, 5 to infinity, and 6 to infinity. So we will also have an array of unvisited elements that will keep track of unvisited or unmarked nodes. So algorithm will complete when all the nodes are marked as visited and the distance between them are added up to the path. So that is the unvisited node will be 0, 1, 2, 3, 4, 5 and 6. Step 1 starts from the node 0 and mark node as visited. As you can see, the visited node is marked as red. So in step 2, it checks for the adjacent node. Now we have to choose. So either choose node 1 with the distance 2 or either choose node 2 with the distance 6 and choose node with the minimum distance. So in this step, node 1 is a minimum distance. So mark it as visited and add up the distance. So the distance will be node 0 to node 1 is 2. So in step 3, now move forward and check for the adjacent node. So which is node 3. So mark it as visited and add up the distance. Now the distance will be node 0 to node 1, node 1 to node 3. That is 2 plus 5 is equal to 7. Now step 4. Again we have two choices for adjacent node. Either we can choose node 4 with the distance 10 or either we can choose node 5 with the distance 15. So choose node with the minimum distance. So in this step, node 4 is minimum distance. So mark it as visited and add up the distance. So the distance will be node 0 to node 1, node 1 to node 3, node 3 to node 4. So that is 2 plus 5 plus 10 is equal to 17. Step 5. Again, move forward and check for the adjacent node, which is node 6. So mark it as visited and add up the distance. Now the distance will be node 0 to node 1, node 1 to node 3, node 3 to node 4, node 4 to node 6. That is 2 plus 5 plus 10 plus 2 is equal to 19. So the shortest distance from the source vertex is 19. Now let's see the limitations and the strength of this Dijkstra's algorithm. So let's see the strength. Optimally guaranteed. So Dijkstra's algorithm is always finds the shortest path from the source node to all other nodes as long as an edge weights are non-negative. So it uses a greedy approach so that ensures once a node shortest distance is finalized, it will never be updated again. Versatility. So the algorithm works with both directed and undirected graph. So it can be adapted for different applications like network routing, GPS navigation, and graph analysis. Next is efficiency. With the efficient data structure like priority queue or mini lib, it achieves an excellent performance, especially in spare or a large networks. Let's see the limitations. First is negative weights. Dijkstra's algorithm fails if the graph contains negative edge weights. So because it assumes once a node is visited, the shortest distance is finalized. So for graphs with negative weight, we can use the Bellman-Ford algorithm instead. Single source only. So it computes the shortest path from one source node at a time. So to find all the shortest path, another algorithm like Flyoard-Warshall algorithm or repeated Dijkstra's runs are needed. Third one is memory usage. The algorithm stores distance information for all the nodes simultaneously, which can be memory intensive for every large graph. Now let's see some real world applications of Dijkstra's algorithm. So first is GPS navigation. So its purpose is to calculate the fastest and shortest routes between the locations. So how it is used? So like mapping service such as Google Maps or Waze apply Dijkstra's algorithm to determine the best route from your current location to your destination. Second is network routing. So its purpose is to optimize the flow of data packets across the computer networks. Third is robotics and AI. So its purpose is to guide autonomous system in movements and navigations. So how it is used? So the robots and self-driving vehicles like Dijkstra's algorithm to plan optimal paths, avoiding obstacles and minimizing travel time or energy consumption within environment. Fourth is complex algorithm. So its purpose is to act as a building block for more advanced algorithm. In this slide, we'll see the optimization and advanced variant. So these methods help reduce the time complexity and make algorithm faster and more scalable. So first is priority queue implementation. So it will replace a simple array or list with a priority queue like binary leap. Next is Fibonacci's leap optimization. So it will use more advanced leap structure called Fibonacci series. So it speeds up decrease key operations, which are frequent in Dijkstra's algorithm. Third is specialized algorithm variant. So tailors algorithm to specific graphs types. So for example, bounded weights, grid, or planar graphs. Next is pre-processing techniques. So it will pre-compute shortcuts or summarize of the graph. So it is used in a road network to speed up the routing. Why Dijkstra's algorithm still matters? Because of its elegant simplicity. So Dijkstra's algorithm solves the shortest path problem using a clear step-by-step approaches. So it's enough for the students and beginners to grasp, yet powerful enough for the complex system. Next is critical infrastructures. So it is not just academic, it powers real world system. It's like transportation, networking, telecommunication, and artificial intelligence. Next is timeless innovation. So invented in 1956 by Dijkstra, it's a classic example for how a single insight can shape a decades of process. So despite new algorithm, Dijkstra remains relevant due to its clarity, adaptability, and performance. Thank you.